classical intuition leads us to expect that particles with kinetic energy must be moving, and hence there will be particle currents or current densities, that is, particles crossing unit area per unit time. We have, however, apparently deduced from quantum mechanics that there are stationary states, energy eigenstates, where the particle has energy, possibly even exceeding the potential energy, but yet there may well be no current associated with such energy eigenstates. If so, this might solve our problem with the hydrogen atom not radiating in its ground state, for example. If there really was no electrical current associated with the particle current of electrons, or at least no changing current, then we would not have to have electromagnetic radiation from the atom. To make any progress here, we need a meaningful way of calculating particle current in quantum mechanics so that we can check these notions. We can start by looking at a mathematical quantity that can tell us the net flow of something out of a volume, the vector calculus operation known as divergence.
In Cartesian coordinates, the divergence of a vector f is written like this, sometimes div of f. Actually, I won't use that notation, but this del dot f, and this is like the gradient operator here, but a vector dot product into the vector f. And the result of that is the rate of change of the x component of f with respect to x, plus the rate of change of the y component of f with respect to y, plus the rate of change of the z component of f with respect to z. And note that the result here is a scalar quantity. Just like the dot product of two vectors gives you a scalar, this dot product in here also gives us a scalar quantity. Now, we can visualize what this means in terms of what we could think of the flux f of some quantity. And by flux, we're thinking of the amount of flow of something. It's a flow such as of mass or of charge, something like that, but it has a direction as well as a magnitude. So we could be thinking about the flow of some quantity like mass or charge through a small cuboidal box. So here's our small cuboidal box with dimensions delta x and delta y and delta z, and centered round about some point that we've called x naught, y naught, and z naught here. Here are our axes, x, y, and z axes. Now, because this vector quantity f represents the flow of the quantity per unit area, then some amount is going to flow out of the front face. Out of the front of the box, this front face of the box here. And the area of that front face of the box is delta y times delta z, the height of the box here. And this would be the value of that vector quantity in the x direction on this front face. So given that this f represents the flow, this is the amount that flows out of the front face. The x position of the front face is x naught, this point in the middle of the cube here, plus delta x over 2. And the y positions of this front face we regard as y naught and z naught. So that's the amount that leaves the box at the front. And this quantity is therefore the x component of the flux multiplied by the area of the front of the box here, the area perpendicular to the x direction. We can also think of this quantity here as the vector product, the dot product between f, the vector flow, dot producted into what we can think of as a vector delta A sub yz. This is a vector, and its magnitude is the area of the front surface of the box here, and its direction is outward from the box, so along the x direction here. The amount arriving into the box on the back face we can calculate in a similar way. In this case, we will be using x naught minus delta x over 2 as the position, of course, of the back face of the box. Hence, the net amount leaving the box through the front or back faces is just the sum of what's flowing out the front minus what's coming in the back. That's why the minus sign is here, because this is coming in the back. And we can also write that by dividing by delta x and putting another delta x up on the top here. And in the limit where we make delta x very small, we assume a small box. This here is just the partial derivative, df sub x by dx. We can repeat this kind of analysis for each of the other two pairs of faces of the box. So adding these three equations together to get the total flow here, we can write for the total amount of flow leaving the small box per unit volume of the box. That is, we're going to divide by the volume of the box, which is delta x times delta y times delta z. Then the result of that is this divergence here. So we've shown that this divergence represents the net amount that is flowing out of the box in whatever quantity this f represents for a very small box, in the limit of a small box, per unit volume. Now, classically, if we're thinking about particles flowing, we can think about the flow of particles in and out of some box, in some little box here, a little unit volume. To conserve particles, we need to have a relation like the following, where S is the particle density and J sub P as a vector is the particle current density. So what we're saying here is that if the amount of stuff inside the box is to increase, then there has to be a net flow into the box. The divergence of the particle current density is the amount that's going out of the box. So we put a minus sign in here to give us the amount that's flowing into the box, and that will lead to a change in the number of particles inside the box. So this is, as it were, the number of particles arriving per unit time into the box, and that would lead to a change in the number of particles per unit time. So the time derivative of the particle density is minus the divergence of the particle current density. So this is the net amount leaving the box without the minus sign, but with the minus sign we get the amount arriving in the box. Incidentally, we are talking about particle current density here, not yet electrical current. We could easily get to electrical current. For example, if we were talking about charge, we could multiply by an E up here, the electronic charge, and similarly, we could turn this into an electrical current here by multiplying the particle current by the electronic charge to get the electrical current. But this is particle current density we're thinking of here. Now, we want to understand particle current in quantum mechanics. And in our quantum mechanical case, the particle density inside our little box, as it were, the equivalent of that S, is just the modulus squared of the wave function inside the box. So we are looking for a relation of this form, but where we have the modulus squared of the wave function in here instead of S. And what we'd like to use that to do is to figure out what this quantity, this vector here, the particle current is in quantum mechanics. To do this, we need to do some algebra, and there's a very clever little trick that we do algebraically at one point in here. Now, we know that this, of course, is just Schrödinger's equation. We've taken the IH bar from one side to the other, but this is just Schrödinger's equation here. And we can mathematically, if we want, simply take the complex conjugate of both sides. So we complex conjugate everything here. We've got a minus sign because we've got the I there when we complex conjugate that. Now, of course, the time derivative of the product of two functions like this, we can split into the usual two parts. It's this psi star times d psi by dt plus psi times d psi star by dt. Then, using these relations here to substitute for the d psi by dt, we use this one, and the d psi star by dt, we use this one here, then we can say that the sum of this plus all of this is equal to 0. all we're doing here is rewriting this equation using these substitutions, and then we've taken everything over to the left-hand side. So far, just a little piece of algebra here. Presuming that the potential V is real and does not depend on time, and taking our Hamiltonian to be in the usual form we've been thinking of for Schrödinger-like Hamiltonian, then this expression here we can rewrite. So h operating on psi is minus h bar squared over 2m times del squared psi plus v times psi. And h star operating on psi star is minus h bar squared over 2m times del squared psi star, and that would be plus v times psi star. I've got a minus sign here and here and here. And of course, this part is multiplied by psi star, and this part here is multiplied by psi. So here's a psi and here's a psi. Well, these two terms just cancel one another out because these are just the products of three functions, and it's the same three functions in both cases. So this simplifies to this following expression down here. So our equation then that we had before has now become this equation. And now we're going to use a very cute algebraic trick. That is one of these things that's easy to prove working backwards, but it's quite tricky to come up with working forwards. This entity here we can rewrite by simply adding in this and minus the same thing. And when you do that, you realize that this expression here, which is the same as that one, is also just the divergence of the difference of these two terms. That's just a piece of algebra, and you can check it out if you want to. So we're going to use this trick to substitute into here. So our equation is now turned into the following one. And this is looking very interesting now because we've got a divergence over on the right here, and this is the rate of change of the modulus squared of the wave function. And this is an equation in the same form as the one that we were looking for, with the modulus squared of the wave function instead of s, as desired. And now we see what the particle current is going to be. So we've got this form of equation. This is, as we wanted, the rate of change of the probability density. And this equation then enables us to identify what the particle current is in quantum mechanics. And it's this expression here. So now, if we know the wave function, we can calculate particle currents in situations where the potential does not depend on time, but that covers a very large range of situations. So solely working from this analogy with classical systems and working with our Schrödinger wave equation and our wave functions, we now have an expression that allows us to calculate particle current densities. Now, this has a very important consequence that we care about here. This expression that we have come up with also works for an energy eigenstate. Suppose then that we are in the nth energy eigenstate. So here's, for some system or other, here's the nth energy eigenstate written out in its full time dependent form, if we like. Then our particle current density as a function of time for this nth energy eigenstate, well, we have our expression for that. We can just write it out here. So it's I h bar over 2m times the wave function times the gradient of the complex conjugate of the wave function minus the complex conjugate of the wave function times the gradient of the wave function. In this expression that we have just written out here, the gradient has no effect on the time factor that is built into either of these two functions here. So the time factors in each of these terms can simply be factored out in front of the whole expression. And they multiply up to unity. So taking the time factors from both of these or from both of these, we can bring them out front here and these just multiply to unity. So in our energy eigenstate of any system, then we can write down what the particle current density is. In this expression that we have then, there's nothing on the right here that depends on time. So the particle current density, Jp for this nth eigenstate, does not depend on time. That is, for any energy eigenstate n, the particle current density is just constant in time. So therefore, the particle current is constant in any energy eigenstate. For real spatial eigenfunctions, in fact, the particle current is actually zero. These two terms are just cancelled exactly.
For a particle such as an electron, the electrical current density is simply the electronic charge times the particle current. Now, a steady current does not radiate any electromagnetic radiation. It might well have both electric and magnetic fields associated with it, but neither of those fields would be changing, so there would be no radiation of power in the waves. This means then that an electron in an energy eigenstate does not radiate electromagnetic radiation. Should a hydrogen atom in an energy eigenstate be radiating? Classically, the electron orbiting round about the nucleus would have a time-varying current. The electron in a classical orbit is continually being accelerated because its direction is changing all the time to keep it in its orbit, and so it would radiate electromagnetic energy. This quantum mechanical result says that the atom in such a state does not radiate electromagnetic energy because there is no changing current. The quantum mechanical picture agrees with the reality for hydrogen atoms in states, and the classical picture does not. We have finally resolved the problem of why the hydrogen atom in its ground state does not radiate. With our strange quantum mechanical picture with Schrödinger's wave equation and all its unexpected properties, we can not only explain all the energy levels of something like a hydrogen atom, and we will do that explicitly later, we can also resolve this old paradox of the previous Bohr model. Once again, quantum mechanics gives a result that agrees with experiment, even if we may be still puzzled by many aspects of how quantum mechanics works.